Okay, so good morning, everyone. So I hope you have recharged yourself and got rejuvenated over the course of the long weekend. And you're ready to start with this new set of lectures from today morning. So it is my pleasure to introduce Professor Cailin O'Connor. She did her PhD on evolutionary game theory from University of California, Irvine. And she is currently the Chancellor's Professor in the Department of Logic and Philosophy of Science at UC Irvine. And apart from many publications, she has also written several books, which include The Origins of Unfairness, The Misinformation Age, which she wrote with her co-author, Professor James Weatherall, who is our next speaker. And so these are, of course, as you would all agree, topics of profound relevance, especially in today's world. And so it's indeed a privilege to be able to hear from her about these topics. So, Cailin.
Thanks. Yeah, hi everyone. So the first talk listed on the program has a different title. This is basically the same talk, but I just changed it a little bit to be a little less philosophy, a little more kind of interdisciplinary interest. The dynamics of inequity. So before we get started, I wanted to talk a little bit about where I'm coming from. You might be like, yeah, why? This is a game theory, an evolutionary game theory, and decision meeting. What are philosophers doing here? Jim, who will speak next, is a philosopher too. So we're in this area called philosophy of science, which is a kind of small area of philosophy. And what people do in that discipline is two different kinds of things. So one very typical thing is studying science itself. How does science work? How can we make it work better? That's something that both of us work on but won't be speaking about at this meeting. And then a lot of philosophers of science also do work that extends theoretical science. So someone who's a philosopher of physics might do work that looks a lot like theoretical physics, but maybe with some more philosophical interest or sometimes things that physicists themselves won't do because of disciplinary norms and rules about what you work on, but might be interested in. And so for me, I'm working on things that are connected to economics, to psychology, to political science, and to biology. Topics like misinformation, how scientific communities work, cultural evolution, and inequity, which is, of course, what we'll be talking about today. And then philosophers of science tend, not all of us, but some of us use methods that come from the sciences, which when you think about philosophy, the method is like, I will just sit down and think about things and then write what I think. But then a lot of us draw on better tools from the sciences. And so I use a lot of different types of tools in my work, like game theory, evolutionary game theory, agent-based modeling, which I'll talk about in all three of these lectures, network modeling, and then also some experimental methods drawn from economics and social psych. So that's why two philosophers are here. All right, so Supra mentioned that I had written this book, The Origins of Unfairness, and everything I'm going to be talking about in these three lectures is connected with this book. And so this was published now 5 years ago, 6 years ago. But it's part of a big project where my group and I have done a number of modeling projects trying to understand how inequitable patterns of behavior emerge. And some of them are still ongoing. Some of them are done. Part of what I'll be talking about today is mostly finished work, but then like the last lecture will be new stuff on the same project. All right. So here's kind of the big picture motivation for all of this. Hopefully it will not shock you to discover that some people tend to get more and others get less. And this is true in basically every culture that's ever been studied. Also true in basically every culture, these inequitable or unfair divisions tend to be supported by social conventions or norms. So it's not just that accidentally some people get more or some people get less, but that we have rules, cultural rules and patterns that persist over time that say people of some type get more and people of some type get less. And usually those rules apply to social categories. And I'll talk a little bit more about what social categories are later. But we're talking about things like gender, race, caste, ethnicity, religion, categories that we recognize as important in our society. So we tend to have these rules like, maybe women do more housework and men do less, or if we're paying people, we might pay people of one race more than another. So we might ask why. What explains the ubiquity or stability of these kind of patterns? Why would it be that when we look at basically every culture, these kinds of rules exist? It's not like we had to have them. They're so natural and extensive that you might almost miss that they're always there, and there's something weird about the fact that they're always there. So that's the kind of biggest motivating question behind this work. So that's what we're gonna be talking about in these 3 lectures. Today, I'm gonna be talking specifically about bargaining models from evolutionary game theory. Why is this the methodology for this type of project? So resource division is best modeled by bargaining. Bargaining is, of course, a paradigmatic type of strategic interaction. So when we're looking at game theory, we're modeling strategic interactions where what you do matters to me and what I do matters to you. And then when we're talking about these patterns, these conventions of bargaining, they're things that emerge over cultural evolutionary time. It's not like tomorrow we go out and we're like, let's now make it that men do more housework, and then we just switch, right? Instead, these patterns tend to develop in societies and then change slowly over time. So that's why this is like a reasonable methodology to be using for this kind of topic. All right. So I wanted to talk a little bit about like how game theoretic methods tend to be used in philosophy and in this kind of project that I'm talking about, because there are some when we're talking about methods that go across many disciplines, there's always overlap in how they're used. But then there tend to be kind of discipline-specific rules and ways people use them. And the ways people use game theory and evolutionary modeling in philosophy tend to be a little different from what you might see in economics and in some other fields. And so I wanted to talk about that a little bit. So here is one main feature, is that in philosophy, people tend to adhere to what is sometimes called the KISS methodology. Has anyone ever heard this before? Okay. Yeah, good. Yeah, Sagar has. Okay, KISS stands for keep it simple, stupid. So the idea is that you develop models that are highly simplified from the real world thing you're trying to model. And of course, that's going to mean that when you look at the models, there are going to be things that don't match the world, and there are going to be ways that those models can lead you wrong. People who follow KISS methodology, and this isn't just in philosophy, a lot of people like this kind of modeling. The idea is that by keeping it simple, you get causal control over your model. You can really understand what's happening in it. And so you use simple models to try to understand causal dependencies. If I change this, how does that change something else? And then you ask, does that tell me about the world? And you have to be careful in asking, does that tell me about the world? So you make some kind of argument or inference about how and whether your simple model tells you about real things. So that's one thing that you'll be seeing in all the talks. They're going to be relatively simple models. Another thing is that philosophy, at the end of the day, is about arguing for stuff, making arguments. And so when we use models, there's a lot of focus on their role within an argument. So I think of a model as a tool that I can use to make inferences. I don't think of a model as a thing that just automatically tells me about the world, but I think of it as a structure that I can study, and then if it has the right type of properties, I can use it in an argument. And you see that also in a lot of disciplines, but sometimes, depending on where you're looking, game theoretic models won't be situated in sort of arguments in the same way. Like I think in computer science, for example, would be an place where you see a lot of evolutionary game theoretic models where it's more like develop the model and just tell the results. Okay, and then there's usually in philosophy like more explicit work to justify why you're using a model, and I think that's because This work is situated in a discipline where not everyone uses these tools. And so people are constantly being like, why would this tell you about that? And so constantly, people like me have to be like, no, here's why models are good for learning about things. Or often my argument is that, like, at least it's better than just sitting down and thinking about it. Now I'm just thinking about it in a different way. All right. So here's where we're going to go content-wise today. So first I'm going to talk about the Nash demand game, which is the game used throughout all the literature I'll be talking about. So that's a model of bargaining. What I'll do first is talk about like how people have used that model to explain the evolution of fairness or fair norms in human societies. Then I'll flip the switch a little bit and be like, okay, people have argued that this model predicts the evolution of fairness and explains the evolution of fairness. But their models are missing something important, and that something important is a representation of social categories, things like gender or race or caste. And once we add that, what comes out of these models is something very different. Now, instead of predicting fairness, they often predict unfairness, unfair patterns of bargaining. And then I'll talk about extensions of these models to understand, in particular, how power can influence patterns of bargaining convention that emerge in cultural evolutionary time, and to really make the argument that unfairness is kind of what we expect to pop out of these models rather than fairness. So that's where we're going to go. Okay, so I wasn't sure how to gear this talk because it's an interdisciplinary group, and I wasn't sure, since I missed the first week, how much background people were going to get. So I just like geared it really low. Please ask questions or give input as we're going along. If you're like, skip that, do more on that. A lot of the models I'm describing, I sort of don't give all the details, but we can stop at any point and fill in those details. And we have enough time to do that. Like, I've set it up. So please like interrupt, and there'll be times I'll stop and be like, let's do questions. Yeah, Jonathan.
So people have seen the bargaining frontier as a pre-talk frontier represented with coordination games so far.
Okay.
They haven't yet seen the Nash demand game representation for when you miscoordinate on the short side.
Okay, good. That's helpful. And so this will be like a quite different representation of bargaining then. And not only that, but I'm going to be using what's called a mini game of the Nash demand game for the most part. So yeah. So this is to say questions and feedback, and I'll keep stopping. Any questions or things right now before we dive in? All right. The Nash demand game. Sometimes the version of the game I'm talking about is also sometimes called like divide the pie or divide the cake. And when people describe it, they describe it like, okay, imagine you and a friend have a resource, let's say it's a pie, you both want as much pie as you could possibly get. You're gonna make simultaneous demands for an amount of pie. And then if they're compatible, you each get your demand. And if they're incompatible because you over-demand the pie, you won't get any, well, you'll get a bad payoff. We'll say you have a conflict then and you get a poor payoff. So that's the game we're talking about. It goes back to John Nash and his work on bargaining starting in 1950. So obviously, this isn't just a representation of like literally standing there and both demanding a resource at the same time. The things at the heart of the strategic situation are individuals who have some resource. They both want more for themselves. But if they're too aggressive, they can't successfully divide it. So there's both a pull towards coordinating, we want to work together to divide it, and a pull towards selfishness. I want as much as I can within that framework of working together. All right, so this game has 2 players. We can just call them player 1 and player 2. The strategies are, we'll say any real number between 0 and 1. So I can ask for 0.1245 proportion of that pie. The payoffs are going to be equal to the demands unless those demands sum to more than 1. And then they're going to be equal to a disagreement point for each player. And in what I'm talking about, that will start as 0. We'll just say you get 0. If you can't divide the pie goes away. And the information the players have is knowledge of the game and of opponent rationality. Though I'm going to pretty quickly switch to an evolutionary perspective, and everything about information will just go away and be fairly meaningless once we move to that perspective. Questions? Is this all?
Disagreement point?
The disagreement point, good. You basically say like there's going to be some kind of conflict outcome or payment, and we assume it's going to be like fairly low. The idea is if you can't divide it, something bad happens to you, you fight, or you just don't manage to like use that resource in an appropriate way. And then you can switch what the disagreement point is based on the game. But yeah, here I'll just say, we'll say it's 0. Yeah. This is saying if our two demand, like say I make a demand and you make a demand, we each are gonna get that unless they're greater than more than 1. So 1 will be the whole resource, the whole pie. And so if we ask for a proportion more than 1, then that's when we can't agree with each other. If our proportions are compatible, we just get them. Good. Anything else? Yeah.
If you underbid from 1, total of your demand is lower than 1, what happens?
This is actually a really good question. So the assumption of this game is it's just gone. But a lot of people have pointed out that's not like a realistic representation of human bargaining, because usually if you had extra, you'd be like, oh, you only wanted a fourth? Let's divide it up, right? There are situations in which it's more reasonable, and we'll just stick with it here. But sometimes my group has done models where we say like, oh, if there's extra, then we'll just assume that kind of gets divided equally or it's split among them in the same proportions or whatever. Anything else? Okay. So this is the basic game. I assume we've done Nash equilibria at this point. Okay. I'll just say it. I'll just say it. So this is, yes, we've done it. Good. The most important solution concept in all of game theory. Again, going back to John Nash's work in the 50s. So in this game, there are an infinity of Nash equilibria. And these are every pair of strategies that perfectly divides the resource. So if I ask for 0.2 of the pie and Subra asks for 0.8, that's a Nash equilibrium. Because if we think about deviation, if someone deviated to demand more, we'd now be over demanding it. We'd get the disagreement point. We're asking for too much, we have a conflict. If someone demanded less, they'd just get less. So everywhere where we perfectly divide the pie is the Nash equilibrium, is a Nash equilibrium. So the sort of first prediction of this game is that when humans have a resource they're dividing, they'll divide the whole thing, but it doesn't give a prediction for how they'll do it, the Nash equilibria. And we could have all of these possible predictions that are better for you or better for me. Now, people don't stop there, because the big move in game theory is once you have a bunch of equilibria, you want to refine. You want to somehow come down to a smaller number of equilibria, and the ideal is often 1 to say what really predicts behavior here. So with this kind of game, the Nash demand game, people have done a lot of different equilibrium refinements. I'm not going to go this route today, but Nash has a solution. There are all these solutions that pop up later, some more famous than others, that give predictions for what will happen in this game under different contexts. We're going to go in a different direction, an evolutionary direction, it might not surprise you. And this thread of literature was motivated by empirical observations of what people actually do in the Nash demand game. So here is what they do. So when you put people in a lab and have them play this game, they almost exclusively demand the 50-50 split. So they equally divide the pie. I mean, you can think about if you were in a lab and I was like, you're just going to play with a person you don't know, how much would you ask for? And a surprising majority of you would ask for half. And this is also fairly cross-culturally stable, which is interesting. In a perfectly symmetric game. Though even if you add asymmetries, like even if you tell people like one of you is more powerful or one of you is special or whatever, in the lab, when you have them play this particular game, the 50-50 has so much pull that it's hard to even get people off it. So I've done an experiment where we were trying to study inequity in the lab, but the pull toward that 50-50 is so strong, you have to set the game up really specially to get people not to go for it. So that's kind of interesting. You know, we could have anything come out in this game. Why 50-50? And then there's this, which is a slightly different but related thing. So if you look at most cultures, there are some kind of stated norms of fairness that support this division, that if it's like, there's nothing special or different about the two people, not only will they ask for 50-50, but that's what they should do. People will say, that's what you should get. You should get half. You should divide it fairly, right? So we have these two observations, and these are empirical observations. And people have asked, okay, well, what's special about the 50-50 split? The basic game doesn't have any reason to say we should go that way, we should be fair, but that is what people tend to do. So that's kind of the motivation for the next bit that I'll talk about, which is going to be this evolution of fairness. Questions or thoughts at this point? Yeah. Oh, sorry, yes.
If you have two individuals, one from some culture, the other from different culture, whose idea of fairness is different. In that case, what happens? How do you modify your?
This is good. So when we move away from like a very, if we're talking about the lab, all this context, cultural context is taken away. And then you tend to see people doing this 50-50 thing. We know that if we look at actual cultures and their details, rules of fairness are very complicated often, and they're contextual. There will be rules like, if this is a resource that you just found, in some cultures it's like you own that once you found it, in others you don't, right? So when we're talking about like a more complicated setup, this is no longer happening. And that's part of what's motivating this whole talk today, is specific rules of fairness that attach to social categories. I don't know that there have been studies where they like had people just play this basic game from different cultures. But I do know like cross-culturally, you tend to get that 50-50 when you take away the context.
I don't quite understand why it's surprising that 50-50 what shows up, because if I were to simply say, okay, how do I, in quotes, maximize what I get, maximize what you get, and also still stay within these bounds, what does pop out is your 50 solution. So
Well, there has to be something more than like, because the sum of our payoffs is going to be the same at any of these outcomes, right? So they're all going to be, from a Pareto standpoint, I don't know if you've done that. Yeah, they're all going to be the same, right? They're equally good. So you have to say something more about why you think 50-50 is special. I mean, it's symmetric, and that's going to play a role in why it's special. But it's not obvious that symmetry should be special, right? It just is because we all feel it is. But we're all the people who would be in this, like this lab. Yeah. So I didn't do the experiment, but basically when people have done these sorts of experiments, they tell them what the structure of the game is. Like, you're gonna have a resource, you can demand any proportion of it. If you over-demand it, you'll get nothing. If your demands are compatible, you'll get it. So they tell them how the game works. Yeah. Yeah, certainly when we looked at the real world, that's not what happens. People don't do 50-50. But so I don't know if anyone's done an experiment where they're like, you guys are gonna clean the house. If you don't do enough, you're gonna be punished, right? How much will you do? Will you do 50%? And it's kind of interesting to think, like, I'm not sure what would happen. I suspect you'd get the fair thing coming up in the lab. Yeah, but certainly in the real world, and that'll be part of the argument here, is like you end up with these rules that are not at all fair, emerging as the rule for how to split things like labor. Good. Yes. Yeah. Good. Yes, so the question was, if we discretize the strategy space, will we get a finite number of equilibrium? And the answer is yes. And we're about to switch to a discrete strategy space for the reason that in evolutionary modeling, working with continuous strategy spaces it's harder, and there's sort of no reason to do it in this game. And so everyone who has looked at this in an evolutionary context, not everyone, but most people have looked at a discrete version of the game. So that's what we'll see next.
How is it different from ultimatum game?
How is it different from ultimatum game? Yes, good. So it's quite different. So basically, the ultimatum game works where it's also a division of resources game, but you assume that you have asymmetric roles where the first, you have a resource again, we'll say it's 1, and the first person offers an amount of that resource to the second person. So I say, I'm gonna offer, let's say it's 10, so that I can just say numbers. I'm gonna offer you 3 of that 10, and then the second person only has the choice to accept or reject what they've gotten. And basically that asymmetry gives like the first person more control over what happens. So the only thing keeping the first person from taking everything is the threat of punishment by the second person. Whereas in this one, it's like over demanding, you both are gonna kind of be equally punishing each other and equally moving first in the demand. Now I mentioned all these like solutions, these refinements to this game, and some of those refinements predict that if you can move first in bargaining, you should get an advantage in this game as well, that if you make the first offer. Yeah, go ahead.
Players are simultaneously demanding, and
Hmm?
and if their demand sum is equal to 1, then they will get.
They get them, yeah.
And if not, then.
And then if not, well, yeah, as long as it's not over 1, they'll get whatever. Yeah, but this assumes simultaneity. And once you move away from that, you can get sort of different things happening.
Even if they demand 20 and 80, then it's
Yeah.
going to be a Nash.
Yeah, that'll be a Nash. Yeah, 20 and 80 would be a Nash equilibrium. 99 and 1, 99.99 and 0.1. Yeah. Yeah. Yes. Of the loss. Mm-hmm. Yeah, good. So the question was, we've set this up as a resource gain rather than a loss. And empirically, what would happen if you talked about this as a loss that you're somehow splitting? And the answer is I'm not sure. And probably someone has done that as an experiment, but I don't know what the result is. I mean, there've been other experiments, and we know people psychologically think about gain and loss differently, at least in some game theoretic contexts. And so it might be that something different happens, but I don't know. Okay, good. Oh, yeah, super. Yeah.
Due to oversight, that people are afraid that they will be perceived as selfish.
Yeah, good. So the question is why 50-50 in the lab but not in the real world? And is it about being perceived as selfish? My 2 cents, this is something that's debated. My 2 cents is that it has to do with people like actually holding fairness norms. I think most people believe they hold to those norms. They think these norms are right and this is what we ought to be doing. They really do hold those. But there are all these contextual things that will override those norms in the real world. And once you move into the lab, those contextual things are gone. And when you look at the real world, when people are being unfair, they often don't even realize they're doing it. So like, they won't even know, like, I offered a bigger salary to that person than that person, or I expect that person to do more work than that person. And so it's that they're holding this norm, and then there's other things in the back of their head that will like say, oh, that norm doesn't even come into play here. Yes. Yeah. Yeah, this is good. So do you know who you're bargaining with? This is actually something that my group tried to do in the lab, and it was a failed experiment, and we're still not sure why. But we tried to see like, okay, could we use markers like gender or status to get people to move away from that 50-50 split in the lab? So first we had to take away the fair split because people in the lab will go for it. Even if you tell them something about like gender or status markers, they'll still go for it in the lab. And so we made it so that it was gonna have to be unfair one way or another, and the question would just be who would be the person getting more. And so that's still up in the air because somewhere something went wrong with that experiment. Or at least we believe, because we got like, in our kind of control, we got results that didn't fit any previous experiments. But so I don't know if you can get people to kind of move away from it in the lab or not. All right, so let's talk about evolution of fairness. Oh, this isn't advancing now. I wonder if it, oh no, there we go, okay. So, motivated by these empirical observations about the specialness of the 50-50 split, people in different disciplines started to try to investigate what makes this special. And so 2 of those people are Peyton Young, who's in economics, and Brian Skirms in philosophy. So they gave some of the more influential accounts of this, like why we have fairness. And so they used evolutionary game theoretic models. As we know, when we're looking at non-evolutionary game theoretic models, we're using rationality assumptions to predict individual behavior. So we're imagining you and I sit down to bargain and we think, okay, what's that person gonna do? Given what they might do, what should I do? And I think they're gonna be doing the same. So that's the sort of framework we're working in. And then when we switch to the evolutionary game theoretic framework, we're imagining something quite different. We're saying we're gonna have a group or a population. They're gonna be bargaining over time. They're gonna bargain with this person, bargain with that person, try it a different way, try it this way. And then over time, they will learn new rules based on their interactions. And of course, these models can also model evolution by natural selection, which I know some of the people are using evolutionary game theory in this meeting to talk more about that kind of evolution. So they switched to this kind of cultural evolutionary model. So they're thinking about humans in a group interacting with each other, bargaining repeatedly, and learning on the basis of what they've done in the past. And as I mentioned, what they do and what I'll do is look at what are sometimes called mini games, where you take the full Nash demand game and you just pare it down to this discretized state space. And they say, let's just give them 3 demands instead of an infinite number. Here we'll say the size of the pie is 10, and they can ask for a low, medium, or high amount. We'll say those are 4, 5, and 6 of the total resource. And so this is a payoff table that shows their expected payoffs for player 1 and player 2 for those demands. We've seen payoff table? Yes, good. So what you can see is here are the disagreement point outcomes. So they demanded more than 10, they get 0. Here are the 3 Nash equilibria, demanding high against low, medium against medium, or low against high. At these places, it's the same thing. They're perfectly dividing the resource. They can do it in ways that are better or worse than each player, or they can do it fairly. So we still get the same strategic structure as the larger game, but now in this tinier game. Any questions about this? Okay. Yes.
Do things change when your inequality is adjusted, right? When you have more skewed strategies only?
Like if I put this as like 1, 5, and 9, for example, some things change. So when you move to the evolutionary model, details of like how often you end up at one or the other change. And the more unfair you make it, the more likely you end up here at the fair outcome, for example. But the sort of qualitative results don't change. Qualitatively, everything stays the same. Yeah. All right, so they've got this mini game in hand, new equilibria. Then, the next sort of step when you're an evolutionary modeler is to set up your population, and you ask, like, how is the population gonna interact? We're gonna have agents in a group playing this game. Who are they gonna play with, and how often, and under what circumstances? So I'm introducing this because in the sort of next section, I'm gonna start restricting who interacts with who in various ways. The most common thing you see are these freely mixing assumptions, that we're gonna have a whole group, and as we go around playing with each other, we bump into each other randomly. So my probability of playing with Supra is equal to my probability of playing with Jim is equal to my probability of playing with Sylvia. So that's the most common assumption, and that's the one they mostly made in this literature I'm talking about as well, the evolution of fairness. Or you could do something like a network. You say, we have a social structure, which is of course realistic to humans. We do have social structures. We don't bump into everyone randomly. There's some people we bump into much more than others. And so you can embed agents in a network structure and stipulate who can meet whom. We won't be doing that today. Another thing people often do is positive assortment, where agents meet their own strategy types with higher probability. So you see that a lot in the literature on the evolution of altruism, people making that assumption. As we'll see in the next section, another thing you can do, which is what I'll do, is assume that like agents who have different types, say those are men and women, meet each other to bargain in the household more often. That would be an example of a different type of population assumption. All right, any questions about that?
The P of matrix you showed was kind of anti-coordination game, sort of.
Yes, yes.
Then does it make sense to talk about a single population in evolutionary context? Usually if you want to get the asymmetric Nashes in anti-coordination game, the interpretation usually comes that you have two populations interacting.
Yeah, good. And so this is going to be part of the point of this literature, and this is part of the literature that like comes to that understanding. So the point is that if you're going to have a whole population playing this game, these two outcomes aren't really going to work for a single population because they're asymmetric. So you're anticipating the whole point. So we'll just go to that and discuss it more. All right, so they look at freely mixing groups. The next thing they have to stipulate is a dynamics. So we're assuming this mixing group playing the game. You have to say how their strategies are going to change over time based on interactive successes and failures. So as they meet others, what will happen? How will they learn over time? So I don't know if you've talked about replicator dynamics. Yeah, so this is the most commonly used dynamics in evolutionary game theory. It was first developed as a representation of natural selection. In cultural evolutionary models, though, it's often just used in a cultural evolutionary model, even though it's natural selection, because you can do more explicit cultural evolutionary models where you're like, we'll assume everyone imitates others who do well with a high probability and doesn't imitate others who do poorly. Or we'll assume that when you try stuff and it works well for you, you repeat it more often. And if you look at those explicit cultural evolutionary like learning strategies, often their average behavior is the replicator dynamics. So it's called the mean field dynamics. You say, if we averaged out what this thing would predict, what will it be? This is almost always the answer. And so then people just use it and say, like, we're representing cultural imitation or something like that. Questions about that? Yeah. Yes. So they give an argument like we can just use this for cultural evolution because it's the average behavior of imitating other people who do well, for example. The other thing people do, and I will talk about both kinds of these dynamics in this project and in my project, are agent-based learning dynamics. I don't know if you've encountered these yet. So, you know, the difference is when we're looking at replicator dynamics, you're assuming you have a very large population. In fact, you assume an infinite population usually. And you're saying we have proportions of different strategies demanding low or medium or high. How will those proportions change over time? In agent-based models, you actually represent individuals, and usually you do a simulation. You're saying there's an individual and then another and another and another, and they have literal strategies, and then they literally meet each other with different probabilities. They literally play. We represent them literally learning. So it's like this is kind of averaging out all the effects of what this kind of interactive structure would be predicted to get, and this is actually instantiating that interactive structure. Does that make sense? Yeah. Yeah. It depends. So people look at both because there can be things that happen in the replicator dynamics that miss what happened in an agent-based context. So for example, if you have an infinite population, stuff doesn't die out all the way. Like a strategy can be doing very badly and it keeps getting less and less and less and it starts to approach zero but never gets to zero, so it could come back. Whereas in an agent-based population, stuff can randomly die out. Even really good stuff could randomly die out of the population. And here, probabilistic effects can matter a lot more. And so you can sometimes get different things, though in the literature I'm talking about, mostly it doesn't matter what kind of dynamics you do. Usually the same thing happens in these models always because it's really about the payoff structure. Yeah. Yeah. Yes. Good. Yeah, so that can be, so the point here is like, sometimes when you're talking about real evolutionary systems, you talk about selection and drift as different forces that can work in these systems. In replicator dynamics, drift is not happening. Drift we think of as like randomness in the system. Here, it's like a good strategy is always expanding, a bad strategy is always contracting. Once we move to agent-based dynamics, something like drift, an analogous force to drift can sort of show up because you have randomness in the situation. So that can sometimes cause problems. So sometimes you'd be like, the agent-based model isn't a good one here because we're trying to think about differences in traits that have a kind of fine difference. And over time, we really do expect the better one to take over, but randomness is gonna overcome that. But a lot of the time, agent-based dynamics are perfectly fine to study whatever system.
Interesting because, as you say, with replicator or imitative dynamics, let's say strictly dominated strategy will asymptotically approach zero, but it doesn't quite disappear, right?
Yeah.
So that's kind of not strong in some sense, it never disappears. But on the other hand, if you tweak the imitative dynamics a bit to change the process of selecting a candidate strategy for imitation, it turns out that you can get asymptotic non-disappearance of strictly dominated strategies.
Mm-hmm.
That surprised me too.
Yeah.
Multicopolis has some papers. So
Yeah.
I don't know, that's just an interesting.
Yeah, just like an interesting aside. Yeah, thanks.
Thank you for
Yeah.
making me think.
So if we had not simplified to minigame
Yep.
and remained within the paradigm of the entire continuous strategies, would adaptive dynamics come in your scheme of things?
Yeah, so if we had done a continuous strategy, there are people who do models with continuous strategy spaces and use these kind of adaptive dynamics. It's just more complicated and it's kind of out of like what I'm interested in. But there are sometimes cases like Steve Frank, who's a colleague of mine in biology, he has pointed at a number of biological cases where he's argued that looking at the mini game has kind of made people miss important real phenomena when you move to the continuous game. So there are some cases where it matters. This isn't really gonna be one of them. Yeah. Okay, good. So I put this up as like a very simplified, like if we're thinking about the replicator dynamics, right, we've got the infinite population. It's, you know, in the middle of the model, it's always gonna be at some state. So here's just one candidate state. Half of them are demanding 5, some are demanding 6, some are demanding 4. When you ask how does the population change over time, well, you're sort of calculating all the payoffs of the different strategies and then the total population payoff, and then the ones that beat that will expand proportional to how much they beat it, and the ones that do worse will contract proportional to how badly they do, and so you get some kind of update. And you may have discussed, you can either do this in a discrete way where you imagine real time steps where you're updating, or you can do systems of equations to do it in a continuous update way. When we're talking about agent-based, this is like, we're moving to a very different representation, as I said. Like, you're gonna be doing a simulation and you literally have these different agents and they have some strategy at the time. Here I've put it like, these are strategies they'll always use, but they could be probabilistic if you wanted. So like this agent always demands medium, that one medium, high. And then you model some kind of process where they literally interact and get payoffs. And then that changes how they learn over time. Okay. All right, so how do we analyze these kinds of models? And again, I apologize if I'm repeating, but I guess, okay, repeating is usually good for learning anyway. So usually one thing you do first is find population equilibria of the models. What are the possible end states of evolution? And finding it in different models can be complicated. In these models, it's quite simple. There are going to be two, and I'll talk about them in a minute. So, what are the places the population can end up that when it ends up there, it does not evolve anymore because all the strategies in the population get equal payoffs. So you do that, and then the other thing you ask is how often do different equilibria evolve? So we have these candidate end states. That matters to your analysis. The other question is which come up more often than others, and that can tell you things about the evolutionary system that matter. So to summarize what they find, they're looking at these models, freely mixing, playing the simplified Nash demand game. They're usually looking at the replicator dynamics, but sometimes agent-based dynamics. It doesn't matter in these models. Fairness, a population of all medium demands, tends to evolve with a very high likelihood across many different versions of the model. The other thing you can sometimes get are fractious outcomes where you have some high demanders and some low demanders, and their proportions mean they get the same exact payoff, and you can also get that showing up, but it shows up less often. So this is what they find, and they take this to be an explanation of fairness. All right, so to give a hand-wavy explanation of why we see this. If we have a population all demanding medium, and this is something people have already been anticipating in our discussion, this is a special population because these are symmetric demands, and anyone who meets anyone will reach a Nash equilibrium. So any single agent who bargains with any other agent will perfectly divide the resource and use all of it. If we have any other population, if we have some lows or some highs or some of both, some agents will meet and they will over-demand the resource, and some agents will meet and they will under-demand the resource. So basically, the all-fair population has this kind of efficiency that evolution is sensitive to. So evolution picks up on that efficiency, and you see it tending to evolve across many of these different variations of the model. Questions about that? Yeah. Further? Yes, yes, so you have stable fractious outcomes. So imagine you had a population where, it depends on the particulars of the payoffs, but maybe a third of them are demanding high and 2/3 are demanding low, and the payoffs are such that they exactly equally balance each other. So the highs are getting high, 2/3 of the time when they meet the lows, and 0, 1/3 of the time when they meet highs, and then the lows are getting low all the time with everyone they meet, and then it's equal payoffs. And so that can happen, but they kind of argued that those are less important, less realistic. Yeah. Yeah. Yes, yes. And so, right, so why do you end up here versus here? If we're talking about replicator dynamics, it has to do with your initial distribution of strategies. Yes, good. And so I can show a little bit what that looks like. Tomorrow we'll look a little more at phase diagrams of these models, but if you imagine this model that we're talking about, and we'll say they're evolving with the replicator dynamics, you can represent all the population states of the model using a phase diagram, which looks like this, where this is everybody demanding low all the time, here's everyone demanding high all the time, and here's everyone demanding medium all the time, and then here's a population state where you have a third of each, and here's half high, half low, and here's half medium, half low. Does this make sense to everyone? Okay, so we can say for every state in the model, where will it go next under the replicator dynamics? And what you're gonna see in these kinds of models is there's gonna be, here's a stable endpoint, and here's a stable endpoint. And then the dynamics, there will be a kind of unstable equilibrium here. The dynamics will carry you about like this. So for most of the places the population could be, it'll go to that fair medium outcome. For some of the places, it'll go to this fractious outcome. So this is what the replicator dynamic system will look like. If we talk about the agent-based system, because it's probabilistic, you can't do this, you can't do a phase diagram, but it'll still be the case that like if you started at random starting places and have them play probabilistically, most of the outcomes will end up here and then a smaller proportion here. Yeah.
In the earlier sort of like bargaining question that we dealt with, it was more groups who were bargaining, so they would form like subgroups, which you know, I was expecting you would say, okay, you're more likely to pair up with these people.
Oh, okay.
Then you end up with lesser power and you fall disciplinary.
Yeah.
So how is your formulation of bargaining different? Because this is a fair one, right?
Yes, so before when I said like when you move to the evolutionary you're in a group, I just meant a group where everyone can meet each other. Yeah, and so I was thinking about this kind of like random mixing sort of assumption. Yeah, though we'll move in the next thing to a different type of groups like categories. Yeah. Yes. Wait, sorry, say it again. Where? Okay, good. Yeah, so imagine, you know, we have a population, we can have different proportions of the different strategies. Our evolutionary rule is however well they do right now, the ones that do well will expand, the ones that do poorly will contract. What we see for this model is for most of the possible places that we could be, medium is doing best. So there's a large proportion of possible states where medium is just outperforming the other ones. And that's because when mediums meet mediums, they perfectly divide that resource. Mediums do well against lows. Mediums don't do well against highs, but the highs are doing badly too. And so at all of these places, the sort of next population update takes us toward medium. And so that's why we tend to get it popping out of the model. Is that helpful? Okay, good. All right, so that's their main result. And then what they do is they say, okay, this helps explain why we have these fair bargaining norms, why in so many societies we'll all say we ought to do a 50-50 split, and why in the lab we see people doing the 50-50 split. And then they kind of expand the model. They're like, okay, there's this fractious outcome, but we can look at all these different sort of realistic conditions for humans, and if we look at these different things, we'll see we always get fairness. So if we put people into networks, fairness is even more likely to emerge. If we have people meeting their own types, it's very likely to emerge. Like if I'm a fair person and I tend to pick fair bargainers for my partner, and then they say, well, we see those things happening in humans, and so that's why we have these fairness norms. So the whole project is thus this explanation of fairness norms. Okay, so that's the sort of previous stuff. Now let's move on to where we're really getting interested. I am taking you through like a history of an area of modeling here. Okay, bad news. Things aren't always fair. Right, when we move out of this contextless lab space, we see thousands of studies in sociology, in political science, in economics, all across the social sciences, showing that things aren't fair, and I could literally give thousands of examples of studies. But we see things like salary and hiring biases directed towards different genders and different races and some other social categories. We can see divisions between high status and low status individuals that aren't very fair. So landowners and sharecroppers divide crops that are grown, and sharecroppers really tend to get a bad deal on that. We see things like attentional biases when the resource is something like the amount of attention a teacher can give students. They'll give, usually more to men in different societies. Division of household labor is a situation where we tend to see unfair outcomes. So depending on the society you're looking at, often if you look at the total amount of labor done in all spheres, women will do more. And then when we look at sales of things that don't have fixed prices, you also tend to see these types of unfairnesses. All right, so this yields a different thing that needs an explanation. So we've just seen these bargaining models that say fairness just pops out of cultural evolutionary processes. You just put people in a situation and have them bargain and boom, fairness. But why do we see so much inequity in the world is then this kind of different question we can ask. So we both need to explain why we have fairness and why we don't have fairness. All right, so a lot of these cases when we look at real world unfairness have to do with what I called social categories earlier. So let's get a little more into what a social category is. So these are categories that are going to be widely recognized within a society and where people in that society use them to guide their behavioral choices when they meet with others. So they can use the category to treat people differently even in the same sort of situation. And there are lots of types of categories. So for example, professor and students, these are social categories, and you use them to condition your behavior to people in a university context, right? And you shouldn't treat students like professors, and you shouldn't treat professors like students. You wouldn't be coordinating your behavior well. So we have many, many types of categories. The ones we're most interested today are the ones that sociologists sometimes call primary categories, because these are the ones that shape our behavior across many, many different domains. So not just in the classroom, they shape our behavior in the classroom and when we're dating people and when we go to the store to buy something and when we hire someone and when we, coordinate with someone to meet somewhere, they shape our behavior often kind of everywhere. And so sociologists look at different cultures and ask, what are primary categories? Across societies, every society uses both gender and age as primary categories. So these ones are ubiquitous. And then for the particular society, there are going to be different ones that count as primary categories. So sometimes it's race, sometimes it's class, sometimes it's caste, sometimes it's religious affiliation. And usually in any particular society, there will be 3 to 4 primary categories. They're the ones that really, really matter, and then many other categories that matter less, or you just use in some cases. Yes?
I don't know if it's possible that percentage-wise, can we categorize what is more in the society, fairness or unfairness?
Oh yeah, so like how often do we see fairness versus unfairness? I don't know that anyone's tried to categorize that to ask like how much does the one norm win or the other norm win? Yeah, I don't know that anyone has been like, how could we quantify that? And I don't know how you do it because it's very hard to say like, yeah, of all the interactions you have and all the ways in which they might be fair or unfair, yeah, it's hard to say. It also starts to be, once you start to measure unfairness in the real world, there's some places where it's like very obvious and then some places where it's very hard to say, are you seeing it? So like, for example, is it unfair if I own something and don't split it with you? Could be, maybe not, depends how you think about it. Yeah. Yeah, usually for class to act as a primary category, it has to be more than economic. It also has to be socially meaningful. So for example, in the UK, there are going to be these like stereotyped class markers. If we look traditionally at the UK, you'd have these stereotyped class markers like dress and speech and all of this stuff that would allow people to recognize class and then treat it as a primary category. If we look at Sweden right now, there's going to be people who have a lot more money than other people, but it's often going to be hard for them to tell. And so it won't act quite like that, if that makes sense. Okay, so, oh yes, yes.
So is it necessary that when it transfers as a primary category, it has to be easily recognizable?
Yeah,
That's
so,
markers for it.
yeah, and it's good that you bring this up because this is something that, is that the time? We're like, oh, okay, good. Yeah, we're going slow, so I'm gonna have to pick up at some point. So this is something I'll talk about in the third talk, is for them to function in the type of way I'm about to talk about, they do have to be recognizable to some degree. So for me to condition my behavior to treat you differently in one context than I would treat a different person, I have to be able to see what kind of person you are. Otherwise, I can't condition my behavior. And so that'll be a key feature here. Good. Okay. So in most of these evolutionary models, you have a single population who interact and evolve. To capture the evolution of behavior when we have social categories, we need to change the model. And what we're going to do is add types, or what are sometimes called tags in economics. So one influential early model of this sort was done by Axtell, Epstein, and Young. It's called the emergence of classes model. So we'll talk about that. So basically what they do is they do an agent-based model. And they say instead of having a population where everyone is identical, now we add an arbitrary tag. It's something that everyone can observe. They can change their behavior based on the tag. So now they'll have a strategy that says, I do this when I meet a blue, and I do that when I meet an orange. Like I could demand high of blue and medium of orange, or medium of both, or low of both, or low and high. So that is how they add tags, but the tags don't do anything except allow others to randomly, like choose different strategies. They don't have any other meaning. So they're not better at producing stuff, they're not more aggressive, they're not more powerful. So now when they meet, they might demand high and low. Oh, sorry. Let me tell you about the dynamics in their model. So they do this agent-based dynamics where they use what's called like a boundedly rational best response rule. And it works like this. The agents all start off without any memories of past interaction. And then as they interact, they gain these memories, and they use those memories to shape their future behavior in a semi-rational way. So these agents meet, they don't have any memories, they're just gonna try something randomly. Say this one demands high and that one demands low. Then they have a memory, and this one's memory is that when I meet oranges, they demand low, and this one's memory is when I meet blues, they demand high. We've all just done it once. If these two meet, this one says, okay, what should I do when I meet an orange? When I've met an orange before, they demanded low. So that means what I should try is the best thing, given that history, all demand high. This one doesn't have any memory, so they just try something randomly. So let's say they try medium. Now they go back, and this one has a memory of blues demanding high, and this one says oranges have in the past demanded low and medium. When this one meets an orange again, they say, okay, what's my best response to this history? This one says, what's my best response to that history? So now they'll try medium and low. And in this way, they develop these memories. They have different memories, though, for the two types. Because, remember, they're conditioning their behavior based on the tags that they meet. And so over time, they'll be developing longer and longer memories. They set a limit. They say, like, they can only go up to 10, and then stuff starts dropping off the end. And basically what happens is that's their dynamic, and then they see what pops out at the end. All right, so this is important. Once you switch to this model where you have tags, you have totally new populational equilibria. So before you had everyone demands fair and then this fractious outcome, now you have three equilibria, and they are the three underlying equilibria of the mini game. So one of the two tags always demands high and the other low. They both make fair when they meet the outgroup, and one always demands low and the other high. So now it'll be like all the blues demand high and all the oranges low when they meet, which we couldn't have in the base model. Within each group, it's still like the one population model. Like when we meet our own type, we tend to demand fair, sometimes we have fractious. With the outgroup, we now have these new equilibria. And the important thing is that these two now look like inequitable or discriminatory outcomes. They're kind of a bare bones representation of discrimination, because you have one group getting more than the other systematically, and there's no reason for it. It's just that they have these different tags. Yeah, here, let's here and then here. Yes, so this happens. It's actually, in most cases, the most likely of the three, though often these two together will, like, it'll be more likely that one of these emerges than that. Yeah, yes.
So
So the tagger type, all it is this arbitrary marker that when we interact, I can say this person is an orange or they're a blue. And then I look at my history and I'm like, okay, I know what oranges do.
So in this case, it is the color.
Yes, it's the color.
So it is
Yes.
static, not dynamic.
It is static. Yes, yes.
Color does not change.
The color doesn't change.
And
Good.
the history that you're taking last past 10 history, you're giving equal weightage to all the histories, all.
Yes, and so I mean, you could vary this, but I think in all the versions of this model that I've looked at, they just treat the histories that they remember as the same, rather than, say, ignoring ones that are old. They just start forgetting some old ones. But all the ones they remember, they're like equal.
So how are you incorporating these memories in your model? I am not able to understand.
So the memories act as, the reason they matter is they tell you what strategy to take next.
Yes, but how are you incorporating in your mathematical model? How are you incorporating?
Oh, so usually, so this kind of model would be run as a computer simulation, and you would just have maybe a matrix where each location is one of the agents, and then there's some number of possible memories they can have, and you just input those memories. And then when you say in their next interaction, you're going to calculate what they do, you use those memories to calculate it.
So you are saying you're taking the past 10 memories.
Yep.
These results are robust to that past 10, 20. It does not matter.
Doesn't matter how many memories you do. It doesn't matter if you do these dynamics or another dynamic, the replicator dynamics, infinite population, small population. Once you flip, because you're always going to have these equilibria regardless of the dynamics. So once you flip to having tags, the important thing is that you now have these new equilibria. Yeah.
The way I choose the best response, I have 10. I know the previous 10 experiences.
Mm-hmm.
The most frequent that I have encountered, do I respond to what is best for that most frequent?
So it'll depend on what they are. So you'll basically literally add up, if I played high against these memories, what would my payoff be? If I played medium, what would my payoff be? If I played low, and you pick the one that gets you the highest payoff. So it'll depend on the differences between them. Mm-hmm. Okay, so what do these outcomes look like, these unfair outcomes? They look like this. The blues are demanding medium of blues, oranges demanding medium of oranges. The blues, when they meet oranges, demand high, and the orange is low. And when we're looking at the memories, it'll look something like this once you get to a stable equilibria. These ones are like, okay, the oranges always demand low, so I'm always gonna pick high when I meet them. These ones, remember, the blues always demand high, so I'm always gonna pick low when I meet them. So those are the stable outcomes of the model. Okay, so this is like a kind of important and deep thing. In the models with one group, the symmetric or fair outcome is special, but when we add tags, they create a symmetry breaker. And they allow new rules, rules like blues always get more and oranges always get less to be efficient. So now in this new model at these equilibria, they're again always reaching Nash equilibria. They always perfectly divide the resource, but they can do it unfairly because they have these tags. So they can coordinate unfair expectations on the social categories. So they find that if they evolve these models, they get these discriminatory conventions robustly. And then a lot of subsequent work, much by myself and others, finds this to be a robust and widespread result. So again, in these models, do it with any dynamics, do it with anything, different population sizes, different variations of the game. You're going to get these unfair outcomes coming up. I want to get into why that happens a little more. So basically, for this to happen, you need these kind of minimal conditions in these models. And I argue there's three things you need in place. So one is you need these tags. So the tags have to be added. That's kind of the magic that gets inequity going. You need conditional behavior. You need the actors to say, when I meet different tags, I'm going to potentially treat them differently. Maybe not always, but I have the ability to do that. And then they have to be able to learn. And whenever these conditions are in place, you will have these inequitable outcomes emerging and being stable in these models. And these, of course, are pervasive and hard to eliminate in real human groups.
So these are necessary and sufficient conditions for converging to the unfair equilibrium.
Mm-hmm.
And
Assuming you have a bargaining interaction, yes. Yeah.
And what do you mean by stable?
Stable, I just mean that, yeah, you can evolve there and then stay there, basically. Like, when you're talking about these population equilibria, the ones you care about will be the stable ones. So ones where once you get there, all the payoffs are getting equal, like within the group, all the payoffs will be equal, and so they'll stay at that. Is that?
Are you talking something about global stability or local stability, something like that, sir?
Here, I mean, here we're going to be mostly focused on concepts of local stability because these are models where you can get different equilibria. I can't draw a phase diagram for this model because it's too big. It has two populations. They each have 3 strategies. Now, like the diagram for it will be like too multidimensional. But it will be the same kind of thing where there'll be a number of initial states that would evolve to each of these outcomes. If, say, we did the replicator dynamics for the medium between groups, for the unfair this way and for the unfair that way.
Just to add to what she was asking,
Yeah.
you mean sufficient content, not necessarily.
Yes, sorry, sufficient, yes. Yeah, because there could be other ways that you could get inequity.
Has it been seen that individually what the effect of each one of them?
Yes, so if you just add social categories but you don't have conditional behavior, the social categories do nothing because they're not meaningfully playing any role in the model. If you have conditional behavior without social categories, what are you even conditioning on? So again, it's meaningless. These two sort of have to be together. Learning by itself, we've seen in the one population model, won't do it. So yeah, they sort of have to be together to get this effect.
If you remove any of the 3, then the unfairness won't happen.
Yes, yeah.
So is it called necessity? I mean, there are other conditions that can also.
Yeah, there could be, I'm sure you could set up other things that would get you inequity. You know, I haven't thought about it that much, but there's going to be something else you could add that would get you inequity. But the point is, like, in this kind of system, you put these things in. Probably you could come up with special ways to block the effect, but generally these are just going to get you there.
I was just wondering how different this is from evolution of prejudice.
Good.
So, I mean, the only thing that I can see is that you have the tags already in place, but for prejudice, you need the tags to emerge.
Yeah, so for the full evolution of prejudice, I mean, you could say, so here, part of the reason I'm not talking about prejudice is that we're not making any assumptions in these models about what the actors are really thinking. Like, to the actors, these tags could be meaningless, except that it's a random thing they've learned to condition behavior on. In the real world, of course, that's not what happens. But the tags could be as meaningless as, like, half of this group is holding up an orange sign and half of this group is holding up a blue sign. And so this model doesn't really track, like, full-fledged prejudice where you have some kind of opinion about a group and you believe things about them and they are this way and we have these stereotypes and they're not as good. And so none of that's really here. But part of what you point out is that, like, without the tags, you can't get here. And so there's some question about how tags themselves emerge. And in the third talk, I'll be talking about that.
Here when we said there are like kind of 3 stable states of the population where either red is exploiting, or they're all playing fair.
Yeah.
We didn't say anything about, say I have a population that where everybody's playing fair. If one of the person starts to, say one of the red starts to exploit, we didn't talk anything about stability to invasion. Can we say anything about?
Yeah, so when I'm talking about these being like stable end states, part of it being a population equilibria is that nobody can change on their own and improve their outcome. Any individual who flips will be doing worse. So you'd have, oh yeah, go ahead. Yes. Well, so yes, they're going to be evolutionarily stable states, not strategies, which is a kind of fine distinction that we don't have to get into. Yeah. All right. So, little history of modeling. Once you add social categories to these models, inequity is not hard to generate. They don't generically predict fairness. Unfairness is also possible. And part of what I do in that book is say, well, really inequity is the more likely cultural evolutionary outcome for all sorts of reasons. I won't get into all of them, but one thing I'm just going to talk about to, like, sort of finish us up is power and its role in the emergence of inequity in these types of models. Okay. So in this paper with Justin Brunner called Power, Bargaining, and Collaboration, what we ask is what happens when you have 2 groups with these different tags and one is more powerful. And we show that powerful groups tend to evolve to get more in these sorts of situations. And then in a follow-up paper with Travis Lacroix, we did the same thing, but with groups where there's variations in power. So in the first model, we said, let's make all of the blues powerful and all of the oranges not powerful and see what happens. The second one, we said, let's have variations, but one is a bit more powerful than the other, or maybe more on average, or maybe it has a few powerful members. So to do that, we had to add power to the models, which is actually like not a totally simple thing to do, because if you just sit for a second and think about power, you're gonna be like, oh, power is a pretty complicated thing. And it actually tracks a lot of different stuff in the real world. So the way we went about it was just tried a bunch of different ways you could add power to these models, all of which seem to capture some things about power. And what I'm gonna do is talk about just one of these today, which actually goes back to John Nash's work on bargaining again. And this involves changing the disagreement points for the actors. So what you do is you say, when the bargain fails, one actor, here will be player one, generically is gonna get more than the other actor. And there's different ways to interpret this. So one thing you could say is one actor has a better fallback position. Just economically or socially, they're in a better position. So if their bargain with the other one fails, it's not gonna be so bad for them. And that would be a type of empowerment in bargaining. Nash also pointed out you could interpret this as coming from threats, where before we bargain, I say to you, if this bargain fails, I'm gonna mess you up. And if I really have the ability to do that, I could make your disagreement point very low. And if you can't do that to me, I would know that my disagreement point wouldn't be as low. And so he was like, that's one way that my like quite literal physical power or my military power could shape behavior in this type of model. So people who have looked at this in the rational choice situation have pointed out that this type of power should change what happens in rational choice. But our question was, will it change what happens in evolution? There isn't initially a reason to think its effect on evolution should be the same as what two individuals would rationally do. Okay, so what we did is we took the same type of model. So the first result I'm gonna describe is a replicator dynamic model. So we have two infinite populations, they have tags, they're bargaining with each other. One of them gets a higher disagreement point when bargaining fails, the other gets a lower. And then we asked, as we keep one disagreement point low and make another one higher and higher, so make this group more and more powerful, how often do they go to these different equilibria, these different possible endpoints of the model? So that's what this figure is saying. We're making the one group more and more and more powerful, and then here, well, this figure really got messed up. It's got all this weird stuff in it. But here is how often they end up at these three outcomes: the fair outcome, the powerful group getting low, and the powerful group getting high. And basically, as we make one group more and more powerful, fair comes out less and less often. The powerful group stops getting low, and they start getting high more and more often. So adding power makes that group conventionally be the one always getting high when they evolve to bargain. So yeah, as I said, that's with the replicator dynamics. We found the same thing, Travis and I, using agent-based dynamics, and I'm just gonna show you one result where we took two groups and we added just one powerful individual to one of them. And so we were motivated by something like, say women on average were less empowered than men in some society, but there are some women who are themselves empowered. So some women are gonna be very wealthy in a society, even if women on average have less money. We wanted to ask, would the entire group, all women, end up disadvantaged in this kind of model? So we say, all right, we're gonna have variations in how much power they could have. This particular one, we're gonna have two groups, they're identical, one individual in one group is powerful. And what we see in this agent-based model is the identical sort of qualitative pattern. As one individual gets a higher and higher disagreement point, fairness between the groups becomes less likely, the group without one individual starts demanding high more, and the group without that individual starts demanding low more. And that's because as they're learning, it's like, I'm running into all of these folks, sometimes I meet that powerful individual, I extend what I learned from them to everyone in the group. So their power extends to the rest of the group. In the previous graph, we were increasing for the whole group. Everyone's getting a higher disagreement point. Yes, the power of everyone is identical, and we're making just one group more and more powerful. And this one, we're just making one individual more and more powerful. One individual in the power, like everyone's identical except one, and that makes this group powerful. Though we also looked at other variations, like everyone has different power. Oh yeah, so this wasn't meant to exactly match that, but we also, for example, looked at models where we selected the disagreement points for the two groups from a distribution randomly. And so in the less powerful group, sometimes you'd end up with people who are more powerful than anyone in the other group maybe, but because this one on average is more powerful, they're still gonna end up at the top more, getting more. This isn't that, this is just the one individual. I thought showing this one's nice because it's kind of, I don't know, it's interesting to see that just that little change can change the whole group's outcome, if that makes sense. Yeah.
In this powerful group, I make next step one more individual more powerful. One more. I increase the number of powerful individuals, but I don't increase the power of the individual. Still, I would probably get this kind of.
You'd get, yeah, so say we, instead of putting that individual's disagreement point up, we just made more and more individuals on one side powerful. I think you'd get a similar effect. I'm not totally sure, but it should be. Yeah. It won't converge to one. Here, so if you look at the disagreement point, at some point it's gonna get higher than the low demand. And once it does that, it will destabilize these equilibria. So so once these are destabilized, there's just one equilibrium left. So we really only look at like it going as high as the low demand. We want to keep the kind of structure of the game the same. Yeah. So here.
So how come like in the initial state the fairness is so much uniform?
Here.
We don't see much deviation in the fairness till maybe 4.
Yeah, so it just has to do with the details of the game, basically. The fact that in this case, we only have one person changing, and so it's not a huge impact on it. And, this is like the one with the most pull. And yeah, like details of how they match and probabilities and, yeah. There isn't some like interesting explanation. Good. All right. So basically what's going on here is if we look at the powerful group in these models, they have relatively little incentive to learn low demands because they don't get a big advantage for doing so compared to receiving their disagreement point. So for them, the difference between low demand and disagreement point isn't that much. And so it's like, you don't have to worry that much about the low demand or making a high demand because you're still gonna get something close to low. And that changes how they learn over time. So if we went back to like this agent-based version where they had these memories, for this agent before we saw that they would demand medium, but maybe if they have a really high disagreement point, their best response will be high. And so that starts to shift how they interact and who learns what about the others. So general takeaway, power asymmetries between groups tend to promote inequity. One of the things I argue is that power asymmetries are the rule in the world. I mean, symmetry is just generally not something you see between groups in the world. Asymmetry is just going to be the rule because symmetry is hard. There's just one place to be symmetric. Oops, sorry. And so given that, I think this helps support this picture where really what you expect to be coming out is these unfair outcomes. I will skip this, but we'll just kind of briefly say people have used this paradigm now to study a bunch of different things like power that can influence bargaining between groups, like minority group size, informational asymmetry, so one group knows more than the other or is better networked informationally, intersectional disadvantage, so where you don't have just two types, you have different types of types overlapping, maybe you have race and gender, homophily, where people interact with their own group more, and dividing the products of joint labor. So you don't just divide something, but first you produce it and then you divide it. And also, and this I'll talk about in the third lecture, the emergence of categories. So how you might get these, where do orange and blue come from in the first place, and why they might emerge in cultural evolutionary time. Okay, so I'm just gonna wrap up. This helps contribute to this picture where unfairness is easy to get. So one thing I argue in this book and elsewhere is that when we think about unfairness or countering it, it's not something we should be conceptualizing as like, we'll do that and then it'll be done. We'll get our society fair and then we just go our merry way. Instead, we think unfairness, we should think of it as something that has a power or a pull. It emerges endogenously via the process of cultural evolution and bargaining. When we have groups bargaining and they have recognizable tags, we're going to expect unfairness to emerge on its own. So given that, if we think about equity, we probably shouldn't think of it as like a state that we can maybe get there. We think of it maybe as a process, because we're engaged in this process of cultural evolution ourselves all the time. And as we learn, we're going to be tending to learn unfair patterns. And so if we don't want to have those, we have to constantly be trying to stop them from emerging on their own, is the argument. All right, so I'll wrap up. When we add social categories, we don't expect bargaining patterns to be equitable or fair in these models. And I think that helps explain why in the world we have this ubiquity of unfairness around categories. I don't always take these models to explain stuff in the real world, but here I think it's such a robust result. And it makes a lot of sense just kind of intuitively once you understand the way categories change equilibria in these models. This helps us square the earlier evolutionary game theoretic work with the fact that we observe so much inequity in the world. Well, it makes sense when we're talking about symmetric interactions. We do expect fairness. When we're talking about situations where we can get these asymmetries, we expect unfairness. So we expect both things in human cultural groups. And then power asymmetries between groups are tending to increase the probability of unfairness. And it may be useful in thinking about equity to be really paying attention to these cultural evolutionary pressures. And it might change the way we think about equity. All right, and that is the end of the talk. And I literally just hit 0. So yeah, there we go.
Can you hear? Yeah, okay. So I was wondering, have you considered the case where tags, the color of tags might correlate to the result of the interactions? Because one could imagine that as people get well off, they sort of, are closer in terms of their tags to that of the other population.
Yeah, good. That's interesting. I have not considered something where it would be like the wealth you are gathering is itself observable. Though when you're talking about something like class, that might actually be the picture you want, that like a tag emerges as individuals become wealthy. The closest I've looked at are models where we assume existing tags, but the power imbalance changes over time as they kind of win these evolutionary races. Like, so power accumulates to groups. But it's not really the same thing. I think that's a really interesting suggestion.
Something we see in experiments is that people have a tendency to punish what they perceive as extortionate behavior or unfair behavior.
Good.
So is there any room for observing similar strategies in this kind of games, say, sort of a development of spite or something?
Yeah, so I haven't incorporated here anything like punishment. And this is really interesting because one thing people argue, for example, in economics, some people think we have a natural taste for fairness, that unfairness like really irks us and we don't like it, which then we should incorporate potentially in this kind of model as people maybe trying to punish those who demand too much of them or something like that. Now, I think in the types of situations that we're talking about, and this isn't something in the models or that came up, but when we look at real world cases of categorical inequity, usually you see the development of a hold ideology to prevent that kind of punishment. So a set of like beliefs about how people in different groups are, and especially about the naturalness of some groups getting less, like, well, women get less because they're stupid, or they're not competitive, or people of that race get less because they're not good at doing that sort of thing, or these people are getting more because they're better at math or whatever. And so once you get all that ideology in place, I think that kind of prevents natural tendencies to push back against unfairness or punish those who are being unfair. But all of that's outside the model. Yeah.
Great. Hello. In the 1993 Peyton-Young paper on the Nash bargaining game, there is, of course, these forces that push towards fairness. And then in later work that deals with more complicated setups, there also tends to be forces that push towards fairness, giving a kind of advantage over the asymmetric ones. And I think Ken Binmore wrote a couple of long books,
yes,
maybe too long,
yes,
but very good, on the topic too. So is this something you're going to get to?
I am not going to get to it because we're going to focus in the next talk more on the evolution of gender.
Okay.
And so that'll be about dividing labor, especially, rather than dividing bargaining. And then in the final one about the emergence of the tags themselves. But yeah, and I just kind of flashed Peyton-Young up there. He has all this stuff on fairness.
He's a very attractive man, as we know.
Yeah, he's very good looking. We should put him up. All this stuff on fairness, and he did stochastic stability come up at some? Okay, yeah, and so he uses this different kind of stability concept in these models to think about the pole of fairness, but also more complicated things around differences. I believe he does differences in power as well, right? And how you'd have that influencing stochastic
there's
stability.
a lot of little twists you can do. Basically, you could adjust the sample sizes and then reflect it in a Nash bargaining solution, and you can play to your heart's content, really.
Yeah. Yeah, but we're not going to do it. And then Binmore's stuff will also not do. I mean, he does stuff on evolutionary bargaining, but he also does a bunch of other models, I think. Just all sorts of stuff on cooperative play and
So good. And we're going to stay with 2 players?
We're going to stay with 2 players, yes. We're going to stick with 2 players in populations for everything. I think for bargaining, I mean, in this project, the only place I sort of deviate that is in qualitative arguments about collective action and the usefulness of these models in thinking about collective actions towards social justice. But it's not very filled in. It's just oh, you can see why you always need social justice movements because you as an individual can't do a lot by yourself. You can see why certain types of social justice movements, like ones that mess up other people's payoffs, are useful in this kind of situation, because if they're getting a lot, you really have to hurt them for them to be willing to shift to another equilibria, so that kind of thing.
Okay, thank you very much.
Have you looked at the role of noise or imperfect information in these systems? Because specifically, the results where you have only one age, even if there's one powerful agent and that shifts the equilibrium, is that result also robust to noise?
So by noise here, would it be something like, I don't perfectly observe your action, maybe? Or my memories aren't good?
Yeah, either type, in the sense that I don't perfectly remember what actions the other group played, or it could be noise in terms of the way, or mistakes in the way I act
Yes,
also.
good. Yeah, so this kind of outcome should be pretty robust to a little bit of noise. So the Peyton-Young framework that John was just talking about, one of the reasons that the way he thinks about these things is different is that he's much more focused on the role of noise. So he thinks about these as systems where, if you had evolution to a convention, you should have experimentation or accidents or errors always kind of bouncing you away from some stable outcome. And if you have enough of those, sometimes you're going to bounce away enough that you go to a different outcome. And so he's thinking more about, an analysis where it's how much time are you spending at different possible outcomes rather than what do you get to with which probabilities. But I, haven't really used that kind of framework. Yeah.
Okay, so maybe we can continue the discussion
Over
coffee
to-
because we've already eaten up 10 minutes.
Yeah, good.